All right, everyone. So welcome to our first session of chemistry. Today, the topic that we'll be looking at in our session one will be the states of matter. All right. So when we talk about chemistry, chemistry basically looks, or it is the study of the composition, structure, properties, and reactions of matter. So if that's what we define chemistry as, it's important for us to understand what matter is. What's this matter that we're talking about? So everything around us is made up of matter. Everything in our physical plane, what we could see and touch, even some of the things that we might be able to see physically with our eyes, it is made up of matter. And matter is defined as anything that has volume and mass, right? Even gases could be measured in terms of volume and they have a mass. So matter exists in different states. That's why I said to those, there's some that we can see and hold and touch, and others that we may not be able to do that with. All right. So we have 4 states really of matter. For our purposes here with the CSEC syllabus, we are going to be looking at 3 states, which is solids, liquids, and gases. But it will be wrong of me to just tell you that there are 3 states of matter, knowing that there are 4. The 4th state is something called plasma, and I'll explain that in a separate slide. But why is this important to our study of chemistry? Because each of these states of matter have different type of properties, and when we adjust things like temperature and pressure, this could change matter from one state into another. Have any of you ever put on the kettle, or you pour a pot of water on the stove and you forget the pot of water on the stove? It boil in there, and then when you remember, you see, oh shucks, you go back there, and sometimes you could go and find the pot empty with nothing in it. Anybody ever experienced that?
Yes, sir.
Right, one of me experienced that. Rivad and Abira didn't say anything, so that tell me that they do be in the kitchen. Is that true?
Nah, it's just ordinary pot boiler.
All right, well, that's good. That's a
I
good.
don't like to be in the kitchen.
You don't like to be in the kitchen. Well, all right, that's good. Well, once you let the pot boiler is a good thing. I fed up to that, and my wife is quarrel with me when I do that. I forget, or I get busy, preoccupied with something else. But what is happening there is that we have something changing states. Initially, the pot had water in it, which is liquid. And what we are applying there, we are applying heat. Heat is a form of energy. Now, as we continue through the slides, we realize that as we supply heat energy, it affects the particles inside of that particular matter that we're talking about. And as it affects those particles, it causes them to either gain energy or lose energy. And that is what results in the change or the shift of a substance from one state to another. Right? Now, if you look at the diagram that I have here, you'd see that if we're traveling to the right, solid to a liquid, we call that melting. Then from a liquid to a gas, which is what happened when you forget the pot on the stove, we have vaporization, right? It turns into gas, water vapor. And then for gas to go to plasma, I still telling you about it one time, you are charging the particles of gas. Now, to help you relate to what plasma is, or that particular state of matter, neon signs. I'm sure you have gone to the mall or you're passing somewhere and a store have a big neon sign up, right? Or your TV. TVs are plasma TVs now, right? You had liquid crystal display, you had the big box on them like what one Maria and I might be familiar with, right? And now you have plasma TVs. Plasma TVs are actually using charged particles of gas. Now, when we're traveling back in the opposite direction, now the opposite happens. To go from plasma to gas, you have deionization, where you are removing the charges away from the gas particles. And then when we have gas going back to liquid, it's been condensed. Everybody familiar with condensation? Everybody know the water cycle and would have heard about that in integrated science, yes? Everybody know that, right?
Yes.
Right. And then from liquid to solid, that's freezing. We know that because we put ice in our fridge in order, well, water in our fridge in order to make ice. Now, as these things happen, notice at the bottom, I have energy, right? It's changes in energy, usually in the form of heat. Now, when we use the word heat in chemistry and even in physics, Rivad will tell you that as well. Heat refers to both hot and cold, right? Even though we define it or we separate it as being hot or cold, heat energy has to do with both heat as we know it as in hot temperatures as well as cold temperatures. So we could either supply heat energy or remove heat energy. And in supplying heat energy, we move to the right, which is shown by the blue arrows. And by removing heat energy, we go to the left, which are shown by the red arrows. So our focus for the remainder of the class would be on the three states: solids, liquids, and gases. All right? Now, according to the syllabus, we need to understand or describe distinct forms of our matter, right? So the three states of matter that we're looking at is solids, liquids, and gases. And there's some important things that or properties that we need to be able to identify. So solids, as you are well aware, have a definite shape and volume. We could tell that this is a table that we're sitting on here, right? Because there's a definite shape. You're not going to get up tomorrow morning and the table going to look different, right? It is a solid. So solids have fixed shapes and a fixed volume. If I was to measure the volume of the table, right? Because that's different from weight, right? It will not change. Tomorrow will be the same, the day after will be the same, the day after that will be the same, right? Why? Because it's the state of matter. Solids have fixed or definite shapes and volume. Now, why does that happen? That is because the particles in our solid are packed closely together in a regular pattern, and they don't move. When I say they don't move, they don't move around. They vibrate in a particular place. So examples of solids would be ice, wood, metal, right? Those are some easy examples that we can think of and visualize in terms of solids. Liquids now, which is the next state of matter that we will discuss, has an indefinite shape, but a definite volume. Now, why would I say it has an indefinite shape? Because if I take water or juice and I put it in a cup, right? And then I take the cup now and I pour it into a pot. And then I take the pot now and I put it into a vial. Every time I change the shape of the container, the liquid is taking the shape of that container, right? So they have an indefinite shape, meaning that the shape could change based on the container they're stored in. But they have a fixed volume, right? So if I took 200 ml of water, or 250 bottle of water, and I pour it into a mug and the mug bigger, it's still the same 250 ml of water, right? If I put it into vials, then it's still, once the vial is large enough to hold all of the full 250, right? The volume remains the same. Now, the liquids, the particles are close together, but they could move and slide past each other. This is why it has that volatile type of property, meaning that it could take the shape of the container, it could change in terms of the shape, right? Examples include things like water, oil, alcohol, right? Any liquids, you all know a lot of liquids as well. Gas now has an indefinite shape and volume. So you see how it's changing as you go from solid to gas. There's a change in that gradient where we're talking about definiteness of shape and volume. Solids definite, shape and volume. Liquid have an indefinite shape but definite volume. And then to the extreme end with gases now, they have an indefinite shape and volume because they could take the shape of the container and the volume as well. So when you buy a aerosol, right? Let's say buy Bop or something to spray the house for mosquitoes and stuff. That's a pressurized can. If you look at the back of the can, you'd see they would tell you not to expose it to heat and not to puncture the tin because it's pressurized inside of there, right? It may not be a large volume of gas, but because it's compressed inside of there, right? It increases in terms of volume. Now, the particles in gas, they could move very freely and they are far apart. But gases, unlike the liquids and solids, are compressible, right? So this is why we have, like when you buy the tanks, the gas tanks for the barbecue pits, right? That's compressed gas in there. If you're into repairing computers, you could buy a can of air, right, to spray out inside the computer keyboard and inside of the CPU and stuff like that, right? So examples of gases include oxygen, carbon dioxide, helium, nitrogen, We could go on and on talking about different types of gases. All right. So everybody with me so far? Everybody understand the main differences between those three states of matter?
Yes, sir.
Yeah?
Yes, sir.
All right, good.
Yes, sir.
Nice. So going on, right? Now, plasma, I promise that I'll explain what plasma is to you. Plasma is the state of matter where a gas is ionized. When we say ionized, it contains free moving charged particles. Now, these charged particles, which you'll learn about a bit later on, are electrons and ions, right? The ionization allows the plasma to conduct electricity, and it also allows them to respond to magnetic fields. It makes sense, right? Because if you have charged particles in there, right? We know with magnets, opposites attract. You have positive and negatives. In order for electricity to flow, you also have a positive and a negative, right? So plasma is naturally found in very hot environments. So like in stars and in lightning, right? Other places where we will find plasma, more artificial or man-made, would be like in our fluorescent lights, right? Those long bulbs that you'd see in your classrooms. These use plasma to produce lights. Auras. Have you all ever seen videos of the northern lights? In places like Ireland and those more northern European countries. I'm sure you've seen it before at nights, and they see the sky with a hue of lights. Want to ever see that, Abira?
Only in movies.
Movies.
Movies
Yeah,
and stuff.
right. Like that's what I mean, like in movies or pictures. Have you ever seen that before? The northern lights?
Yeah.
Right. So that is a same thing. Plasma interacting with the Earth's magnetic field. Plasma TVs, I was telling you about plasma TVs. They utilize plasma technology to create images on the screen, right? Fusion reactors. These are experimental devices used to produce energy through nuclear fusion. They contain plasma as well. And the sun and other stars. Most of these celestial bodies are composed primarily of plasma, right? So we know what, or have an idea what plasma is now. Now, in order to explain the properties of these various states of matter, there are two things that we have to look at. Now, the video that I shared with you guys on the WhatsApp group, I spoke about the particulate theory of matter. But there's also another theory called the kinetic theory. Anybody knows what kinetic, the word kinetic means or implies or suggests?
So I think movement.
Movement. Very good one, Maria. Movement, right? So when we talk about kinetic energy, we're talking about motion, right? So this theory, and this is how I need you guys to think when you're doing this, right? You want to relate the abstract information you're learning to something that you already know. So it's easy for you, I don't like to use the word remember. I want you to understand. Because if you understand something, then you don't need to necessarily remember it too much because you understand how it's works, right? So the kinetic theory helps us to explain the properties of the various states of matter. And it has to do with movement. What movement we talking about here? Well, we said that matter is made up of particles. So the particles in each of these states of matter are moving. And this is why we could use the kinetic theory, which focuses on movement to explain the properties of matter. You all understand that now? That makes sense? So you see how we understanding what it is we're talking about. We're not just rambling and going on and on. And the kinetic theory states blah, 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 yada, yada. No, we want to understand it. Because if we understand it now, it doesn't matter how they will ask a question. We understand this thing. So we can answer it based on our understanding, not based on what we remember. So let's go into this now. We're talking movement. So the kinetic theory explains the properties of your solids, liquids, and gas based on the behavior and movements of these particles. And as we continue, we will learn about different types of particles called atoms, molecules, and ions. Now, in this diagram here, you could see what I was describing before. We actually started describing this kinetic theory or using the kinetic theory to explain why solids have a fixed shape and fixed volume, while liquids have an indefinite shape but a fixed volume, and why gas has an indefinite shape and indefinite volume. Now looking at this GIF we have here, right? The solids, you could see the particles are regularly arranged and they're not really moving about much, right? They have a slight vibration. But then when you look at the liquids now, they have a little more movement. So they could slide past each other. So that's why they don't have any definite shape. They're going to take the shape of their container. Gases, on the other hand, they have a lot of energy. They're all over the place. They like how you're going to primary school around recess time and sharing and with a set of snacks and candy and things. You see how that's look? Running wild all over the place. That's what's going on inside the gases. All right. So what we're going to do now is we're going to look at a summary of each state of matter, because this is important. They like to ask questions about the properties of each of these or to compare them at times. So what we saw with the solids, we saw that the particles are closely packed in a fixed orderly arrangement. In terms of movement, they vibrate. So they have a slight, because everything moves. Nothing, even though it appears to the eye that it's not moving, there's movement in everything. All right, everything moves. Your tree, which you think don't move, moving, right? Because it's move when the breeze blow and sway, right? It had to move in terms of the roots traveling through the ground in order to collect water and nutrients and stuff. They move, right? Rocks that you think don't move, again, made up of matter. They are solid. So the particles, the atoms, the ions inside them on a very minuscule level, if we go down in there, you will find way more activity happening than meet the eyes, right? So particles in solids, they vibrate in place, but do not move from their positions, right? And now we're going to talk about the properties. Now we have 4 properties here, and we need to be able to explain each of these properties according to kinetic theory, right? What is causing the definite shape and volume of the solid? Well, the particles not moving around. They're more or less fixed in a position, right? And that's what helps maintain the shape and volume. We established that already. But why is that so? Why is it staying like that and not moving around like the liquids or the gases? The reason for that is because there are strong intermolecular forces keeping them in a fixed position. These are forces of attraction. So you know they say like opposites attract, right? As we go on and we learn about different particles in matter, we'd realize that in solids, there are positively charged particles, and then there are negatively charged particles that are moving between the positively charged particles. And this lattice-like structure, lattice meaning like, you know, rows and columns, is what is keeping this definite shape. It's strong intermolecular forces. So the particles cannot move out of position because the forces of attraction is so strong that it's not going to move. Understand now? Now, high density. When we talk about something being dense, what is your understanding of something being dense? Anybody? Somebody tell us something dense. Anybody?
I don't know if I explained it, but so that like it's hard to break through.
Hard to break through, yes. And why would something be hard to break through? You're on the right track.
Is it solid?
It's solid, but what making it solid? Something, what will make it hard? It compress, it packed together. You have a lot of things packed into there. So let's take, for example, a pillow. A pillow has
Filling,
yeah,
sponge.
you have your filling and your sponge inside of it, right? But some people like soft pillows and some people like firm pillows. Agreed?
Yes, sir.
Right. Now, the firmer the pillow is, what is causing that pillow to be firmer? What is packing more into it?
More sponge,
More, right, you're packing more sponge and more filling in it. As you pack more sponge and filling inside of there, the pillow is becoming not just firmer, but denser. Exactly. So when we talk about density, density is a result of close packing of particles. That is what results in high density. So when you look at the diagram with the solids and you look at the other two with the liquids and the gases, solids have in let's say in we could use the word in per square foot or in per square inch, right? There's a lot more particles. If we cut out like a cube out of the solid and we take that same shape of cube and we put water in it, and then we take a microscope now to check how much particles in that same exact thing. The water is going to have more particles packed inside of there, just like the pillow I was describing, right? You stuff a whole set of sponge inside of there where the pillow now start to feel like a rock stone, right? You ever went on a bed or a pillow and pillow real hard? It's supposed to be it's supposed to be soft, right? But if we put too much of sponge inside of there, it'll become too hard, it'll be too firm, right? And some people don't like firm pillows. They say, better sleep on the ground, boy. This pillow real hard, right? And that's because why? It is dense. It has a high density. And that high density is a result of packing particles inside of that pillow. So the high density that we see in solids is a result of particles, or the close packing of particles rather, right? Now notice, as we're doing this kinetic theory, we're talking a lot about the particles, how they are arranged, how they pack, how they move, because it has to do with movement of these particles inside of it. Now, another property of solids is that they are incompressible, right? You can't compress them. If I take the table and I try to squeeze it together, right, it's difficult to compress it. I might need to go and get you know, sometimes I see my little daughter watching these videos on YouTube, and it have like these compressing machines, and they put in all kind of different little gadgets and thing inside of there and squashing them. You watch that too, right? Yeah, I expected either you or Ravad to watch that, right? And a truck driving over thing now. Abira, she's 4 years old, so you and a 4-year-old watching the same thing.
But so my 4-year-old son is watching.
Kids do that too, but don't worry, I just watch them too, Abira, so don't feel no how. Sometimes I just want to see what will happen, right? So solids, some of them, if you look at the videos, you will see some of them is very difficult to compress, right? Whereas, you know, you put some kind of bubble or you put a pack of ketchup or something and see it splash and it splat together. If we take something like a marble and we put that in there, you'll see the machine going and going and going and going, and then eventually, after a while, then it might be able to compress it and break it up. But the more dense the substance is, right, meaning it more solid, right, it's going to be more difficult to compress. Why? You must always ask why. Why? Because there are not a lot of free spaces between these particles. They jam up next to each other. It's like you take every when I was a teenager, probably from Form 3 or so going forward, my parents used to send me to Barbados. My dad's side of the family from Barbados. And when you go to Barbados, what we call maxis is called Z vans or ZR vans or something like that. I can't remember, right? And they used to pick up people, and all the seats in the maxi will be full. And then I'll see the conductor still pointing and calling people, right? And they will stop and they will start to put people would sit on top of each other and things like strangers. I don't even know how that dynamic used to work. And stand up in the aisleway, and they used to pack them Z vans and thing like beyond its capacity, right? Now, this is what we're talking about. When we talk about solids, they don't have any kind of free spaces in there. Everybody jam up right next to each other, right? And this is what makes it difficult for it to be compressed. When you look at those videos, Abira, and you look at where they're gonna do like a juice box or a bottle of water or something, right? Those are compressed quite easily. Why? Because when we look at our diagram of the water, according to the kinetic theory, you have free spaces between the water. They could slide past each other. Oil, all those kind of liquidy stuff could compress very easily, right? Do you know that in your car, Most cars, the trucks have what we call air brakes. The cars have what we call pneumatic brakes. So they actually use fluid, and it's the compression of these fluids is what they use in order to brake the car, to slow down the car. When you mash the brake in the car, you actually compressing brake fluid, right? It's not water, it's a special type of fluid, right? With a certain level of viscosity. And as that compresses, it gets harder. Now it is not as it's easier to compress than water. So that's why your brake will feel kind of soft. But it helps in terms of closing in the pistons not the pistons, the brake calipers, so that it could hold on to that this pad or the split. The pads could hold on to the display and slow the car down, right? Rigidity. Solids are described as being rigid, meaning that you can't break it something easily. Why is that? Because you have particles in fixed positions and strong forces between them that makes these solids rigid and resistant to deformation. So somebody could take a bottle and you could squeeze the bottle and turn it and stuff like that. If you fill water in a balloon, you could squeeze the balloon and the water will go up to the top or it'll come down below, right? But with solids, if I give you a piece of iron, right? Not everybody can take a piece of iron. You might have a few people in the world that might be able to bend an iron. And it depends on the tensile strength of the iron. But that rigidity is because of those fixed particle positions and the strong forces that is holding them together. Everybody all right with that?
Yes, sir.
So we understand the properties.
Yes, sir.
So what we want to take away from this slide is that we need to know the properties, and we need to be able to explain why solids have those properties. All right? So we're going again. Liquids now. So you see how liquids bouncing around and moving around all here in this diagram here? The particles are close together, but they're not in a fixed arrangement like the solids. They're not arranged in rows and columns. These particles could slide past each other. And the properties, as we described before, is that they have what we call indefinite shape but definite volume. The reason for that is because the particles could move, so it takes the shape of the container, but they remain close enough, right, to maintain a constant volume. They're not like the gases running wild all over the place. In terms of density, they have moderate density. This is why when I give you the example with the pneumatic brakes, right? You could mash the brakes in your car and that's going to compress the fluid, right? It is not as difficult as, trying to probably compress a rock or a diamond, right? So you could apply pressure. You don't need a machine to do this. You could apply pressure with your foot and that will compress the fluid inside of there. And the compression of the fluid is going to then close in the brake calipers. Calipers is like two little clips like to the top of the inside a wheel where the tire will rest on. They have a what they call like a rotor, this a rotor pad that's turning while the wheel moving. And then you have disc pads on either side. And when you mash the brakes, you actually squeezing in a valve like that, squeezing like that in order to slow down. If you look at your bicycle, if you ride a bicycle, when you mash your brakes on a bicycle, it have these two rubber things that's kind of pressing on the tire. Ravad, Abira, right bike? One of Maria, you must know that. We fix the endless bike and thing.
Yes, sir.
Right. So it's the same principle, right? No. So what liquids have indefinite shape and definite volume, moderate density. They have slight compressibility, right? So it means that there's a bit more spaces between the particles compared to solids, and this allows for that compression. That's why we could use our foot and mash the brakes, and you don't need some fancy machine to do that. Fluidity, the ability of the particles to move past each other now is what gives liquid that ability to flow. So if you throw a solid on the ground, eventually the kinetic energy will die. I'm talking about that you exerted when you throw the solid on the ground and it will stop. But liquids now, if you throw down a bottle of water fall on top of the table here, like problems because the water going to run off the table and fall on the PC on the side, and then I have no PC to do class. Why is that? Because the particles could move past each other. They have what we call fluidity. Solids don't have that, liquids have it. And that's because why? The particles could slide past each other. They have enough energy to move past each other. Now, there was something we talk about to the solids that I keep saying. They have strong forces of attraction between them. Now, based on what we're seeing here with the liquids, do they have strong forces of attraction between them?
No, sir.
No, they don't, right? The forces of attraction between the particles in a liquid is less than that of a solid, but is enough to keep them in a definite volume, right? So when we're talking about comparing solids, liquids, and gases, these are the things that they want to talk about, right? So CXC will ask you, well, compare and contrast solids, liquids, and gases. So then you talk about volume and shape. You talk about forces of attraction between particles. You talk about density. You talk about compressibility. You talk about fluidity. Liquids are fluid, solids are not. And this is how you compare and contrast, right? So you're looking for similarities and differences when you're comparing and contrasting. Good. Next, we have gases. Now look at this diagram with gases. These particles, just like the children are telling you at recess time in the primary school, especially the lower forms, them running wild all over the place. The particles are far apart with no specific arrangement. It's hard to get them to line up, right? The particles move freely and rapidly in all directions. So particle arrangement and particle movement, you could describe that for each solid, liquid, and gas. We could then go on to talk about shape and volume. Particles in the gases move independently. So they fill the shape and volume of the container that they're in. If you put them in a big container, they will stretch out and go all over the place, right? Just like the children. I always somehow, when I see this, I just think of primary school. You take them and you put them inside a room, they're still going to run wild all over the place. You take them and put them in a smaller room, they're still going to run wild all over the place. They're just going to move and fill up the spaces wherever they're in, right? When I go to my daughter preschool on an evening, you know, activities done and things, they're all over. You're not going to find them like us in secondary school and even older in tertiary and things, sitting down in rows and columns, right? Why? The reason for that I like to allude is that kids just have more energy. They just have energy. Their energy do finish for whatever reason, right? They just keep going and going and going and going. I just had to keep exercising to keep up with my daughter because I don't know where she's get energy from. And she can sleep for 3 minutes and she go and get up and she ready to go, right? So just like the gases, the particles in the gas have a lot of energy, so they move in independently. Anywhere you put them, in a small room, a big room, a savanna, they're moving all around, right? Now, because they are widely spaced, they are going to have what type of density? Lower or higher? Anybody? Low density, medium, or high? Low, right, Abira? Agreed? They are going to have a low density. And the reason for that is because the particles are not compressed like the solids. They're not close together. They are widely spaced. So it's like you take a pillow and, you know, sometimes people, they say, oh gosh, what I have to do over my pillow? My pillow dead, right? You lie down on your head, just sink down in the back of that pillow. Why? Because after a while, sometimes either the sponge come out or the sponge lose the sponginess and you have a lot of spaces. So when you lie on the pillow now, there's no support. Agreed? Yeah, I do like when my pillows get like that. As how to get a either stuff more thing inside of that or something. Right? So that's low density. High compressibility. We say solids were low compressibility. Why? Because they don't have no space between them. It's like the bus that the Ivana tell you about in Barbados. They jam pack everybody inside of there and everybody sitting down like this. You can't even move left or right. Right? But with the gases now, that's like you take a TT ride share and as you alone, you have the whole back seat for yourself so you can open out your legs, you can spread out your hands. It have real space. Right? So they have high compressibility for gases. Fluidity, right? So we notice that solids didn't have fluidity. Liquids have fluidity, and gases have real fluidity. Why? Because they have the rapid free movements of particles, allowing the gases to flow easily. And there's a lot of spaces between them. So the more spaces, the easier for them to move. Understand? Right. So everything that we discuss shows how the kinetic theory describes energy. We talk about energy, right? The solids, strong forces of attraction, but the molecules themselves do not have a lot of energy to break those forces of attraction and move around. Liquids, a little more energy, less forces of attraction between them, but still enough to keep them to hold their shape. Gases, lots of energy. Breaking them forces of attraction, they go in wherever they want to go, they're independent, right? You ever go to church or you go to a function and you see them little children and all learn to walk and thing? Nobody can hold them. They going, running, right? That's gases. And this energy that we talk about and the movement of the particles is what is influencing and creating the distinct properties that we just described in solids, liquids, and gases. Everybody understand that?
Yes, sir.
So let's recap what we just talked about. So arrangement of particles, movement of particles, and what it looks like. So solids are close together with regular patterns. Liquids close together but random arrangement. Gases are far apart, random arrangement. Movement, solids vibrate on the spot. Liquids, they move around or slide past each other. Gases move quickly in all directions, right? And you could draw these if they ask you to draw a diagram to show, right? For solids, you put them in regular rows and columns. Liquids, a little kind of, disarrange it a little bit, not to arrange. Gases, you want to show more spaces between them, right? Less particles, more spaces. Now, here are some important things that we need to note. A solid at a given temperature has a definite volume and shape, but changes in temperature is going to affect this. So solids usually increase slightly in size when heated, right? Expansion, and usually decreases in size if cooled, contraction. So you was ever home during the day, right? Let's say Abiru or a van, or they end up, or they get to stay home a day or something. Their parents say, well, I'm going on the road to come back. And you're home in the house and you sit down and you're watching TV. And then you hear a certain noise just so, like the roof making noise. Making noise like that. You ever experienced that before?
Yes, sir.
Right.
Yes, sir.
The reason for that is because as the day gets hotter, the roof expands. And then the opposite happens in the evening. Sometimes in the night, for coming out to dusk dark and thing, you hear it making that same noise again. That's because as the place cools, you have contraction happening there, right? So it contracts. That's what makes that sound. Liquids at a given temperature also has a fixed volume, right? But we know that it takes the shape of the container into which it is poured. But just like solids, liquid volume is slightly affected by changes in temperature. As we change the temperature, right, the liquid would evaporate. The particles themselves get enough energy to break past that barrier of being a liquid and they change state. Now, gases at a given temperature has neither shape nor volume. It will take the shape of the container in which it is placed and it's spread out evenly within it. But unlike solids and liquids, the volumes of gases are affected very significantly by changes in temperature. Why? Because you are supplying more energy to these already energetic particles. This is why you do not heat cans, right? You'd see on the spray can, they say keep away from heat because they supply energy inside of there. Those particles will cause the can to explode, right? Liquids and gases, unlike solids, are relatively compressible. We saw that. This means that their volumes can be reduced by the application of pressure. When I talk about the pneumatic brakes in our car, we are applying pressure when we mash the brake with our foot, right? So you are changing the compressibility, or you are compressing liquids. Gases, however, are a lot more compressible than liquids, right? This is why, like when you look at the CNG, because they have a tank and they could compress a whole set of gas inside of there that will be able to fuel the car, right? So let's summarize the main points. Right? Kinetic theory helps us to explain the ways in which matter behaves. It provides evidence that is consistent with the idea that all matter is made up of tiny particles, and the theory explains the physical properties of matter in terms of movement, right? Movement. The main point is that all matter is made up of tiny moving particles invisible to the naked eye. Different substances have different types of particles, atoms, molecules, ions, which we will talk about later on, and they all have different sizes. The particles move all the time, even though you are not seeing it. The higher temperatures, the faster they move on average. Why? Because you are supplying energy. It's like giving them kids chocolate to eat, more energy. Heavier particles move more slowly than lighter ones that are given temperature, right? So that's kinetic theory. Now this diagram, when I upload the book for Juana Maria, this diagram was taken from the concise. You learn this, you're good to go with everything we just talked about, right? So what I used to do is actually used to look at this, list out all my properties on one side of the page, and then I'll just leave some headings for solid, liquids, gas, and then I would just box it in, right? Like a box and plot diagram, and I would learn this. So any question that come on comparing the three states of matter, off the top of my head, I know shape, volume, density, compressibility, arrangements of particles, forces of attraction, energy possessed by particles, movement of particles, and I know how it behaves for each state of matter. So this is an important table that summarizes everything that we just talked about. So you learn this table, you know that whole kinetic theory and how it applies to state of matter. All right, everybody okay with that? You understand that? Right, so you're making sure and learn this table for this topic, right? Good. Now we have to talk about changing states, right? How we could use the same kinetic theory to explain changing states of matter, going from solid to liquid to gas, gas to liquid to solid, right? Now, a substance could exist as a solid, liquid, or gas. Even the strongest substance, you know, supplied with enough heat, you could melt a solid, and we all know this, right? You go in the grocery, you buy candles in case light go during a hurricane or power outage. You light the candle. As you apply heat over a period of time, all of that going to melt, right? So when we apply heat to a solid, right, it melts, or sometimes it could then evaporate or boil, right? So if you take ice, if you apply ice, heat to ice, you are going to melt it. Then if you continue to apply heat to that water that is formed, it's going to boil, and then it's going to evaporate and become a gas. Now to do the opposite, we have to remove heat. Remember I was mentioning that at the beginning. You could either supply heat to move it right along the gradient in order to move from solid to liquid or gas. To go back in the opposite direction, you have to remove heat. That's why you take the water, put it in ice trays, and put it in the fridge, right? You're removing heat. By dropping the temperature, you are removing the heat energy. So we say that when you take a gas and you remove heat energy, it condenses to form a liquid. And then when you take the liquid and you continue to remove heat, you freeze it, right? So you're cooling down the substance. Now, there are some solids that turn straight to a gas when heated. The name for that is called sublimation. Examples of that is called hot ice. You all know about hot ice?
Yes, sir.
Right.
Yes, sir.
Right. Hot ice. Long time when the Flavorite man driving around. Well, now it have, I don't know, was it brand or the signal, but we used to have a Flavorite man driving around with the bell ringing, the little bell. You know, it have ice cream, nutty royal ice cream, sandwich, lolly, all of them things. Inside of that little cart that he's pushing around, he has hot ice. Hot ice, right, is frozen carbon dioxide. But you see, frozen carbon dioxide, once you keep it at that low temperature, remains a solid. It keeps the things inside of there very cool. if we try to increase the temperature, it doesn't go to a liquid. It goes immediately into a gas. Right? Now, sometimes as young fellas, we take the hot ice and we put it in a bottle and shake it up with a little water and thing, and that's kind of cause a chemical reaction and cause it to explode. Why? Because it changes straight from the solid to a gas, and then sometimes the amount of gas particles inside of that bottle is too much, and by shaking it up, you're supplying energy, right? So you shake it up and you throw the bottle and you bow and you blow off the cover or you blow the bottle in two, right? Because you supply too much energy to those gas particles. Another example is iodine. Iodine is something that could also sublime. It is usually a shiny purple black crystal, but when you warm it, it goes straight to a purple vapor, right? Immediately. It does not go through that liquid phase. It skips that phase and go to a gas. Now, if you're going the opposite direction from a gas back to a solid, we call that deposition. So sublimation and deposition, those are the opposite ends of the same side, if you want to call it that. So I have a table here where we're talking about the kinetic theory and changing states, right? Now, this is important. You have to understand what happens when we apply heat to the solid. Now, when I apply heat to the solid, remember, heat is energy. You are supplying energy to those particles that are held down by strong forces of attraction. And when I supply energy to them, they are going to get more energetic. And as they get more energetic, they break those forces of attraction. So the heat causes the particles to vibrate faster and push the neighbors away, causing the solid to expand. As they gain more energy, the forces of attraction weaken. The particles themselves have more energy than the forces pulling them together. And as the forces of attraction weaken, that regular structure that we looked at starts to break down. And the particles now start to move around each other. You ever melt butter? You ever making cake and melt butter? And you probably,
Yes.
right. And you notice sometimes you have to put it back in the microwave because on the outsides melt and then you still have a solid piece of butter in the middle. Or if you take a spoon and you start to turn it around, that solid piece would melt because the heat from the others would melt that piece. You ever notice that? That's a perfect example of what I'm talking about here. As you supply the heat, the forces of attraction weaken and it breaks down the structure. So it starts to be in between a liquid and a solid. You have liquid and solid in there, right? Now, at a certain point, the temperature is going to remain constant until everything melted. That's what is happening during melting. And that temperature at which that happens at is called the melting point, right? Now, in a liquid, you have forces of attraction between them. We said that it's just not as strong as the solids, but it's strong enough to prevent them from becoming a gas, right? Now, as we heat the liquid, the particles get excited. They start to move faster and faster because energy increasing. When you think about the water, when you put the water to boil in the pot, first you'll see a little bit of bubbles on the outside of the pot. Yes? And then as you leave it longer now, the water going to start to bubble. Like you go and boil macaroni, you have to heat that water properly before you put in the macaroni. You're waiting until you have a rolling boil, they call it, right? Where you actually see the water moving. And this is what is happening. You are supplying heat energy and you are supplying energy to those particles. So they're moving faster. And as they gain enough energy now, this is why they're bubbling up, right? They get to the top and they start to get enough energy to break free of that barrier and become a gas. So it causes the liquid, the excess energy causes the liquid to evaporate. Understand? Now at that boiling point, again, temperature is constant. So the particles in the liquid now is gaining enough energy to form gas bubbles within the liquid. That's why it's bubbling, right? The temperature where this vapor pressure of the liquid equals atmospheric pressure, right? So they ain't reached to the point as yet where they could break through, right? So with more energy supplied, these particles tend to gain enough energy to break free of the liquid now and they become a gas. Now, if you want to go back in the opposite direction now, you have to take a gas You're familiar with the fractional distillation column where you heat a liquid and then you cool it down and then condense. Why? Because when you cool it down, now you're taking away the energy. As you take away the energy, the particles can't move all over the place again. They start to get back closer together. And as they get closer together, the forces of attraction that once caused them to be a gas that was weak starts to get stronger. And they condense and go into a liquid. And then if you go further now and we cool the liquid, we put it in the freezer and we drop the temperature, you're removing the heat energy. So the particles don't have that energy again to move around. So it freezes and becomes a solid. Everybody clear on that?
Yes.
Right. So this is an example of what I was telling you about. This is dry ice or hot ice. Frozen carbon dioxide. Changing directly from a solid to a gas when they're heated without ever becoming a liquid. Right? This is because you have a rapid spreading out of the particles called sublimation. The opposite of this, which you are cooling it from a gas to go back to a solid, is called deposition. Right? Carbon dioxide and iodine are the two that does that. So this is a summary of your changing states. Now you need to learn this diagram because very often you'll find questions where they would leave some of these blank and you need to fill them in. So what I used to do is I used to practice drawing the whole diagram. Get a sheet of paper, you draw it, you draw it until then you don't have to look at the book to draw it. You automatically know how to draw this by memory. So our short video explainer. Now the funny thing with this is that sometimes I don't know, I find when I try to play this, we don't get the audio, just as I thought. So what I will do is I'll open it in a Internet Explorer browser. And that means we have to change our shape.
Hey guys, welcome to another video. Today we're going to be covering the kinetic theory of...
1 second, sir. Right, so we want to move on now. We're going to talk about what we call heating and cooling curves, right? So there's a heating and cooling curve, and we need to be able to interpret the graph of the heating and cooling curve. It's basically what we just described a short while ago, right? About the kinetic theory and what happens to the particles as we supply heat and we remove heat. But this is often shown on a graph. On your graph, your time is always on the x-axis, right? And you have your temperature for this particular graph on the y-axis. The y-axis is your vertical axis, the one that's going from top to bottom. Your x-axis or the horizontal axis runs from left to right. So what you are doing is you are adding heat, right? When you're doing your heating curve, and then you do the opposite. You remove heat when you're doing your cooling curve, right? So when we add heat, we're going in the forward direction, right? As you increase the temperature, you have the solid, the temperature of the solid. Usually they will do this with something called naphthalene, right? In the lab. Some of these experiments, Juan and Maria, I will get on YouTube, and so you can look at the videos because we won't actually get to do it. But they will keep the solid, and usually while they're heating the solid, we'll have a thermometer inside of there so we could record the temperature at intervals, right? So maybe every 20 seconds or 15 seconds, 15 seconds intervals, 10 seconds intervals, you're recording your temperature. And you'll record the temperature as you continue to apply heat. Now, what you'll notice is as you apply heat to the solid, the temperature is going to continue to rise. But then you're going to get to that point that Abira and I was discussing or saying earlier with the butter, when you're melting butter, where you end up with both solid and liquid. So the end's still liquid already in the butter, but then you still have some solid chunks inside of that. When you get to that point, what you will notice with the thermometer is that the temperature starts to remain constant. So as you're tracking this in your table, Now you say you're going in intervals at 10, yeah? 10, 20, 30, 40, 50. You might find when you reach 50 seconds now, between 50 seconds to 100 seconds, the temperature just reading the same thing over and over and over and over and over, right? That point, which is your melting point, and if you're going in the opposite direction, your freezing point, the temperature is going to remain constant until all the solid has melted. But if you do not cooling curve, it will remain constant until all the liquid is frozen. When that happens, then the solid is now liquid and the temperature will now continue to rise. Now, you might find that the time for which the liquid now have to continue heating, if you look at the graph from here to here, is significantly longer. Well, not longer, but the temperature needed in order to heat this liquid enough to it to become a liquid and gas is significantly larger. It requires more heat to be added. Because look at the short span between here to here. Not a lot of temperature, well, it depends on the type of solid was needed. But then we have this long run here, right, where we increasing the temperature in order to heat up the liquid. And then the same thing happens again. You get to a point where the liquid, right, has those rolling bubbles as that we talk about, a rolling boil, right? That's how they describe it in when you're listening to like a chef talk or something. And what happens here is the temperature remains constant. It remains constant at that boiling point until all the liquid has boiled, right? And in the opposite direction until all the gas has condensed. And then we move to the gas. So your heating curve is drawn when the temperature of the solid is measured at intervals as it is heated and it changes state from a liquid to a gas, right? The temperature is plotted against time as we go up. The cooling curve is drawn when the temperature of our gas, so you're going to start from the gas now and come back down, is measured at intervals and is cool as it cools and changes from liquid and into a solid. You're plotting your temperature against time in the same way. Yeah? Now, important things to note, we say that the melting point is the constant temperature at which the solid changes state to liquid. Your boiling point is the constant temperature at which the liquid changes state into a gas. It could be the opposite as well too, right? Freezing is what we will refer to when the liquid is changing into a solid, right? And condensing is what we refer to when the gas is changing to liquid, right? You see I have that here. Now, gases tend to liquefy, meaning turn into a liquid, if the pressure is increased enough, right? So you hear about LPG, liquefied petroleum gas. That's when you increase the pressure of the gas and it becomes a liquid. And then as you release it now, you release the pressure, the gas changes from a liquid back into a gas. The gas cylinders used for camping stoves and barbecues contains liquefied petroleum gas, LPG, under high pressure. As soon as the pressure is released, you open it, the liquid turns back into gas. So for transportation, it's highly pressured and it's liquid. As you open that now to use to cook, it turns back into a gas because you're releasing the pressure. Right, we have another video here on our cooling curve. So let's take a quick look at it and then we continue with our slides. So in that video, it was important to reinforce that at different points of the graph, like between B and C here and D and E there, there's a mixture of solids and liquids at the melting point. And between D and E, there's a mixture of liquids and gases at the boiling point. All right, so moving on. So particulate theory of matter, what it is and evidence of it. So you guys saw my video, right? I sent a video in the group kind of as a prelude to your chemistry lessons. Everybody saw that? You looked at it? What I talked about inside of that video. Anybody remembers? There was two things to give evidence for the particulate theory of matter. Anybody remembered what it was about? No? You all hear me, right?
So, one was osmosis.
right? And the other one was diffusion. So with the particulate theory of matter, similar to the kinetic theory, right? It's based on that same fact, that premise that all matter is made up of particles. And these particles are always moving, and temperature, right, which is really heat energy, affects the speeds of their motion. Now, particles, right, or matter rather, has empty spaces between them, and the particles have forces of attraction between them. Now, the process of diffusion and osmosis provides evidence to support the fact that all matter is made up of particles. So whereas the kinetic theory helps us to describe the properties of our three states of matter, the particulate theory of matter supports or provides evidence that matter is made up of particles, right? So one is to describe the properties and states, the properties and characteristics of the three states of matter. That's a kinetic theory, because we're talking about motion and what happens when you supply heat and when you remove heat, and what are the properties and why they have these properties. But to get to all of that, we had to agree upon the fact that matter is made up of particles, of tiny particles. And diffusion and osmosis gives or supports the fact, or provides evidence that all matter is made up of particles. Right? Let's go take a look at that. So diffusion. Now diffusion can happen in gases as well as in liquids. Both particles in gases and liquids are capable of diffusing. Diffusion really is based on the particulate theory of matter. It states, or it tells us, that particles could move from an area of high concentration to an area of low concentration. And the reason for this is because the particles are always in constant random motion, and they tend to spread out evenly through available spaces until some form of equilibrium is reached. So they don't want to be jam-packed in one area, right? They want to be able to spread out until everybody have enough space, or equal amounts of space, if you want to call it that. That's what we mean by equilibrium is reached, right? So in that video that I shared with you guys, right? In that video that I shared with you guys, I gave an example for you to try at home, which was the spraying or the air freshener perfume in a corner of the room, right? Very often, like on a morning, again, my kids don't think ready for school, or come outside, or warm up the car and thing. Very often it's our people that will pass, ladies, and they have one little perfume on their body, mist and that kind of thing. And after they pass and then they reach 4 or 5 houses up the road, the whole street smelling of the perfume they wear, or the body mist they wear, or whatever. You ever experience that? Somebody come in, I'll be real, one of them show it that somebody come in and say, that smell real good, boy. I asked my friend, what was that brand mist she get, or where she get that cologne perfume, sorry. Did that ever happen to you?
Yes, sir.
Right. Why?
No, sir.
That never happened to you? Never somebody come in the class and they smelling sweet, and the whole classroom start to smell like them? No, never. I remember when I was in school, they had this cream that the girls and thing used to buy. One, you might remember this. I think the name of the cream was Razak. You know that cream, it? It's a real high scented, flowery scented cream. And all them girls in my secondary school used to use that. And when they go in the back and thing class and they finish, right? And teacher in front. And they might have a little bottle, just to come in small bottles, and they put it on that cream, because now it's evening time. When evening time reach, everybody looking to walk home and walk down the road and thing after. So the girls and them, they fixing up themselves to walk down the road. And the teacher didn't used to like that. She like them combing their hair and doing them kind of thing when our class still going on. When class done, all they see about that. And they used to pass around the cream, but it used to sell them out because it have such a high scent that even though in the back of the class or in a corner, as time passed by, the whole classroom going to start to smell of that rasa cream. It's a distinctive scent. I will never forget that scent. Just the other day, I think I see it in Pennywise and Shimo. I say, you know about this cream? And she laughed. She said, yeah, I know about that. I say, all them girls and I used to have a bottle of that cream when I was going to school. So what I'd really saying is that the scent is spreading out evenly through the room, although it starts in one corner. As time go by towards the end of the period, eventually the whole classroom smelling of that cream or that scent, right? That accounts for diffusion, right? That's what we refer to when we're talking about diffusion. Now, in the chemistry lab, we're not going to use no rasa cream in order to do that. The experiment that they usually use to show or provide evidence for diffusion, especially in gases, is an experiment involving concentrated ammonium. Now, ammonium is a very pungent smelling gas. You will know the scent of ammonium. Another gas that's very strong, the CNG that we use in the gas stations is actually an odorless gas, meaning that it doesn't smell. So in order for safety purposes, in order for them to detect a leak, they include another gas with it. I'm trying to remember if it's I think it's sulfur, you know. I can't remember entirely, but I believe they include sulfur. Sulfur or hydrogen, and it's not hydrogen sulfide because that's acidic gas. Sulfur. Sulfur is another nasty smelling gas, right? But they include sulfur together with the natural gas. So if there's a leak, you're bound to smell it. You ever pass by a gas station before they started doing the work? Why, I don't know if you guys is reach as far as Arima, Malabar Lights there going through by Kukurit, the gas station and have a big extra foods there. They used to have an automotive, right? Automotive components there. You don't find around there smell kind of funny. Sometimes you get a real bad scent.
Yes.
Usually,
Right.
we never pass any glasses.
Right.
Nah, not really much.
Okay. But if your glass down, one of Maria says she get a scent. The scent of that is because automotive components, they have a CNG line and there's use CNG there, right? And maybe there's a escape of gas. I'm not saying there's a leak, but somewhere gas escapes. And that said, my wife is always asking what's that. I had to tell her, say again, that is the CNG leaking, right? But because CNG doesn't have a scent, there's include sulfur in it, right? So that you would know when there's a leak. So all I have to say is I kind of stray a little bit there. The ammonium is a very pungent gas, but this experiment is going to show a reaction between ammonium, right, and hydrochloric acid, right? Ammonia solution really, and hydrochloric acid. So what they will do is they will take this test tube, see the test tube here, and on one side they'll take a cotton and they'll soak it with it has to be concentrated ammonia solution. Concentrated means that it's going to have more particles, so that those particles is going to travel faster, right? And concentrated hydrochloric acid, right? So the opposite of concentrated is diluted. Concentrated means that there's more particles of either the ammonia or the hydrogen peroxide per unit space then, right? And you will put the cotton in on either side of the test tube and cork the test tube simultaneously on opposite ends of the test tube. What will happen is the ammonia will react with the hydrogen chloride and it will form something called ammonium chloride, which is a solid. It is a solid cloudy formation you're going to see, right? And you will see that forming inside of the tube. So the ammonia is giving off ammonia gas, and the hydrochloric acid is giving off hydrogen chloride gas. But those gas particles are going to travel in the tube, and when they bounce up, right, they're going to react with each other. And the ammonia, because it's positive, is going to be attracted to the chloride because it's negative. And those two are going to join together and it's going to form ammonium chloride, which is a solid. Now, solids don't always have to be, when we're talking about interaction with gases, doesn't always have to be something that we could physically touch, right? Once it starts to become, as you've seen in this experiment, a cloudy solid white formation, we describe that as being a solid. It's a precipitate, if you want to call it that. All right, so we're going to look at this experiment. Well, the other plate in our next order. Right, so that was an example of the ammonia hydrogen chloride experiment. right? So a second. Right, so now what we need to understand about this experiment, we notice that on one side of the tube, you had the cotton with the concentrated hydrochloric acid. This was the right-hand side. And then on the opposite side, you had the concentrated ammonia solution. Now, what they usually ask is, well, why is the ring forming all the way up on the side, right? The reason for that is because some of the particles is traveling faster than the others. The ammonia particles are clearly much faster than those of the hydrochloric acid because it's able to travel all the way across the opposite side and almost meet the hydrochloric acid, closer to its end. So the particles of the gases are diffusing through the air in the tube and they are colliding, right? So you see all the dots here, this represents the ammonia particles and they are diffusing very quickly along the tube, fast, right? And then the hydrogen chloride particles are diffusing quickly, but they're not as fast as the ammonia. When they get to the middle, the ammonia and the hydrogen chloride particles collide. And as they collide, you'd see the reaction here. This is a equation showing the reaction. You are forming ammonium chloride, NH4Cl, and it's a solid, right? Now the ammonia particles diffuse faster than the hydrogen particles, so the reaction is closer to the source of the hydrogen chloride particles, which is on the right side of the tube. Very often we say they like to ask you to explain or draw on it where the ring was going to be formed and write an equation for the reaction that is happening, right? So these are some little things that we have to pay attention to. So that's why I included them in as part of your slides. Now, apart from diffusion in liquids, diffusion could also happen. Apart from diffusion in gases, diffusion also happens in liquids. Now, this here is an example of what we call potassium magnate 7 crystals, or potassium permanganate is another word that we use to describe it, in water. Now, I gave an example of our experiment to use as a lead up to our class today by taking food coloring and putting the food coloring in water and observing it, how it will change the color of the water. In our laboratory or school setting, they will actually use this potassium permanganate. Now, what they will also look at is not just the diffusion of the crystals in the water, but they will also look at the effect of the speed of which it will happen in cold water versus hot water or warm water. All right, so we're going to take a look at a video on that experiment now. Right, so just to explain what happened in the video, we have the tiny crystals or the crystals packed together before dissolving. You have water particles that are randomly moving and have spaces between them, right? Now what's going to happen is that the crystals is eventually going to, the crystal itself is going to decrease in size because what's happening is that the crystal particles are separating from each other. And as it separates from each other, diffuses into the spaces between the water particles. Now you notice that she did one with cold water and one with hot water. In hot water, the water particles themselves have more energy. So they are moving along a lot. So as they move along a lot, they're going to bump into those crystals. And that's why it's going to spread faster in hot water as opposed to the cold water. Yeah? So that was diffusion. The next thing we need to talk about is osmosis. So we're going to look at the definition, examples, and uses. Now, osmosis is the movement of solvent particles now. We're talking about usually water through something called a semi-permeable membrane, right? And this is from an area of low solute concentration to an area of high solute concentration. Now, when we do a we'll see it. I'm going to show a video after, right? Now, this occurs because the solvent particles move randomly and tend to spread out evenly, balancing the concentration on both sides of the membrane, right? Now, let's just say, for example, we have a dilute sucrose solution, and it's separated from a concentrated sucrose solution. So a dilute solution is going to have more water molecules as opposed to a concentrated solution. A concentrated solution, sucrose solution, is going to have a lot more sucrose in it, right? That's the difference between dilute and concentrated. Now, if we have those two, the concentrated is on the inside of the semi-permeable membrane here, and on the outside is the dilute sucrose concentration. What is going to happen is that you're going to have a movement along that gradient from dilute or high solute concentration to low solute, right? Now, the concentrated sucrose solution can't move through the membrane, right? Now, a semi-permeable membrane means it's selective. It could only allow movement in one direction. So what you will notice is that eventually the level of this dilute sucrose solution is going to drop. Why? Because it's going to move inside of here until it balances it out, until both of them are the same level of concentration. All right? Let's take a look at it. Now, in living cells, the same thing happens. The same thing happens in living cells in our bodies, where we try to manage the concentration, the water concentration inside and outside of the cells. So the solute is what we would have when you have your sugar dissolved in it, right? Let's take a look at the video, and then we talk about it after.
Before we can talk about osmosis, let's do a quick review about solutions. Solutions have a solute, like salt or sugar, that gets dissolved in a solvent, such as water. Okay, so now that we know what solutions are, check out this experiment. This tube has a membrane right here that separates two solutions. The solution on the right has a higher concentration of solute, and the solution on the left has a lower concentration of solute. Make a hypothesis. What do you think is going to happen? Now, watch what happens over time. Did you notice that the level of blue solution on the right went up and the level of solution on the left went down? Can you explain why this occurs? This happened because of osmosis. Osmosis is the diffusion of water across a semi-permeable or selectively permeable membrane, such as the plasma membrane that surrounds cells. During osmosis, water diffuses down its concentration gradient, from higher to lower water concentration, just like other molecules or ions. You can also say that water moves from an area of lower solute concentration to an area of higher solute concentration. Sometimes this confuses people, but if you think about it, it makes sense. For example, a solution with 1% solute is 99% water, but a solution with 20% solute is only 80% water. The higher the solute concentration, the lower the water concentration, and vice versa. In our experiment, water moved toward the area with the higher solute concentration. Here's an easy way to remember the direction that water will flow during osmosis. Water follows solute. If you can remember that, you're basically all set. But we do use a few terms to describe relative solute concentrations that you need to know. One, hypertonic. If we are comparing two solutions, the area with the higher solute concentration is hypertonic. Water will always flow across a membrane toward the hypertonic solution. Remember, water follows solute. Two, hypotonic. This is the solution with a lower solute concentration. Water will leave a hypotonic solution by osmosis. Three, isotonic. If two solutions have the same solute concentrations, they are isotonic. The amount of water moving between isotonic solutions is equal, so there is no net change in water amounts between the two solutions. Now, let's look at some real blood cells undergoing osmosis. These cells are in a hypotonic solution. Make a hypothesis. What do you think will happen? The cells popped because water moved into them by osmosis. The cell's cytoplasm has a higher concentration of solute than the distilled water they are floating in, so water rushed in and caused them to explode. Now, let's look at the opposite effect. Here's an egg that has had its shell removed by being soaked in vinegar overnight. We are going to soak it in corn syrup, a hypertonic solution. Look at how thick the corn syrup is. That is because it is very concentrated with sugar, a solute. Let's speed this up. Watch what happens as the egg soaks in the hypertonic corn syrup. Notice how it shrinks and becomes shriveled up like a raisin. This is because it loses water due to osmosis. To practice more with osmosis, check out the interactive experience at biomanbio.com, linked in the description. If you are enjoying these videos, please feel free to like and subscribe.
Right? So what we saw with osmosis. So basically, water follows solute. The solute would be whatever ingredient was added to your water to create the solution, or was added to a solvent to create a solution. And what you have to realize is that the water particles will always move from an area of high concentration, where there's a lot of water, to an area of low concentration, where there isn't. So when we talk about a hypotonic solution, you're talking about a solution that has a lot of water, right? A hypertonic solution is where the water is going to leave and go to, right? So you see here they say water exits the cell causing shrinkage. Now, this is not necessarily too important in chemistry. This kind of leans a little bit more towards biology, but we still need to be able to understand how osmosis happens in living organisms. An important takeaway here is that water, when we're talking about osmosis, is the movement of water molecules from an area of high concentration to an area of low concentration. Everybody okay with that?
Yes, sir.
All right, nice. Right?
Yes, sir.
So in living cells, the cell membranes, right, are differentially permeable, selectively permeable. This means that it only allows some substances to pass while blocking others. And this is what helps to maintain the cell's internal environment. So if you take, there's an experiment they do with the potato, right? They dig a hole in the potato and they leave some water in there, right? And you realize that after they come back and check, it will the water will disappear. If you guys are accustomed cooking, right? You're making curry potato, you know, my wife will say the potato is suck the water. What already happening there is osmosis, right? So you'll find that when you're cooking the potato, if you're doing curry potato, you'll have to add water to it. Not so, Juana Maria?
Yes, sir.
You have to continuously keep checking the pot and adding water so that it don't dry up too fast. It'll dry up faster than if you're boiling rice or something else, right? So that's osmosis in living cells, right? Now, I think this is the last slide. We almost finished here. Types of particles that make up matter. Now, this is just an introduction to types of particles because we're going to go more in depth in it in our next lesson. But basically, we have atoms, which are the smallest unit of an element that retains the chemical properties. Inside of atoms, you have subatomic particles, which we will look at. But in terms of an element that retains the chemical properties, not changing from the original element it is, we have atoms. Molecules can be formed when two or more atoms come together. So for example, the oxygen molecule is made up of 2 oxygen atoms. Water is made up of 2 hydrogen atoms and 1 oxygen. Carbon dioxide is 1 carbon, 2 oxygen, right? And then you'll have ions, which I mentioned earlier. These are atoms that are charged because they either lost a subatomic particle called an electron or gain electrons, causing it to become negative. When they lose it, they become positive. If they gain it, they become negative, right? More of which we will do when we look at different groups on our periodic table. So we're now at the end of our session. I have a summary of questions here for you to do to test and make sure that you understood everything that we did. This is what you're going to do for homework. And I also have some suggested answers on your next slide, right? But I want you to answer in your own words, right? First, so you're going to do this in your book, in your exercise book, right? You should be able to answer each of these questions. If you can correctly answer each of these questions, then that means that you understand or remember everything that we covered with the topic today. All right. So let's wrap up. Any questions from anyone?